Continuing with the theme of the previous modules, we're going to look at confidence intervals in the t-distribution by using the Framingham data and considering the Framingham cohort to be the true population of interest, and we're going to sample from the Framingham cohort to draw inference about the mean of BMI at baseline in the Framingham cohort. So if you recall, in the previous module, I called X BMI at baseline, and I assumed that it was normally distributed with mean mu and variance sigma squared. And then when I constructed my confidence interval, I assumed that sigma was known such that I could construct a 95% confidence interval as x bar plus or minus z 1 minus alpha over 2 times sigma over the square root of n. So sigma is known in this example. And this is our confidence interval. So this z1 minus alpha over 2, what is that guy? I have a standard normal distribution centered at 0, and I'm constructing my confidence interval. If I'm using a 95% confidence interval in this case, I would have alpha equals 0.05. I want to construct my interval such that 95% of the mass lies in here. So to construct my confidence interval, I want to find the value of the standard normal distribution such that 2.5% of the mass lies in this tail, and consequently the other 2.5% lies in the lower tail. So the way that this value is denoted in statistics, it's denoted z 1 minus alpha over 2, where alpha is equal to 0.05. So in our case, for a 95% confidence interval, it's going to be z subscripted with 0.975. Now, I say that we're looking at confidence intervals from z to t because when sigma is known, I construct my confidence intervals using this z value from the standard normal distribution. And the way that I find that z value is I use the inverse normal command in STATA. We're going to see that here in a minute. But it's usually not the case in practice. Usually we don't know sigma. Usually sigma is unknown. And when that is the case, what we have to do is we construct a 95% confidence interval. In the same way, I do x bar plus or minus, but now since sigma is unknown, I have to base my confidence interval off of the t-distribution. So I use a t-distribution with n minus 1 degrees of freedom, where n is my sample size, and I use that same cutoff, that 0.975, and now it's times s over the square root of n. At this point, let's go ahead and open up STATA, and we'll start constructing confidence intervals. In this exercise, we're going to take a random sample of size 20 from the Framingham cohort. Now in this lab, I might recommend that you try to obtain the same random sample as I do. So if you want to make sure that you get the exact same sample, type in set C2 right now, once you've read in the Framingham data. So now we should be able to take the exact same random sample by typing in sample 20 count. Once you've taken your random sample, type summarize BMI1 to get a picture of what's going on in your sample. See that we have sample mean x bar equal to 25.0, sample standard deviation x equal to 3.2. Now let's construct a 95% confidence interval if sigma was known. We saw how to do this in the previous tutorial. And I use the exact same formula. Just do x bar minus 1.96 times my standard deviation to get the lower bound, and then plus to get my upper bound. Now I want to show you I could obtain the exact same result by replacing the 1.96 by this inverse normal command, and I would plug in 0.975 because you remember I wanted the value of the normal distribution such that 97.5% of the mass of the normal distribution was less than that threshold. So I use that inverse normal command to obtain this. Notice if I were to just type di inverse normal, notice if I were to just type display inverse normal 0.975, I come up with basically 1.96. So to get the exact same confidence interval, I can use the inverse normal command. And this is somewhat useful because what if I wanted a 99% confidence interval instead? Then I can replace this with inverse normal 0.995, hit enter, change this guy to plus, and then I can obtain a 99% confidence interval. So you can use this inverse normal command to obtain, various different types of confidence intervals if you don't want to be just stuck with the 95% confidence interval. We're going to start by taking a sample of size 20 from the Framingham cohort. In this exercise, it might be useful for us all to have the same random sample, so type set seed 2 if you want to take the exact same random sample that I take. And then we're going to take a sample of size 20 from the cohort, deleting the rest of the observations in the Framingham cohort, so that now we have a sample of size 20. In my sample cohort, I want to summarize BMI at baseline. And you can see I get an estimate of my sample mean x bar, it's about 25.0, and my sample standard deviation s is about 3.2. And now I want to construct a 95% confidence interval for mu. We saw how to do this in the previous lab exercise. Let's go through it again really quickly. For the first confidence interval that I construct, I'm going to assume that sigma is known and that it's equal to 4.1, the value of sigma in the general Framingham cohort. So this is exactly the same as the confidence interval that we constructed in the previous tutorial. However, let's say I didn't want a 95% confidence interval. It would be nice if I had some flexibility here. We can use the inverse normal command to get that flexibility. So if I replace 1.96 with inverse normal 0.975, what that's going to do is it gives me the value of the standard normal distribution such that 97.5% of the mass is less than that value. And this guy comes out to be basically 1.96. So using the inverse normal command instead of just plugging in 1.96, you can see that I obtain basically the exact same confidence interval. Any of the differences are just due to rounding error. You can see that the actual value of the inverse normal function at 0.975, it's very close to 1.96, but it's not exact. So instead, if I wanted to get a 99% confidence interval, I would replace 0.975 with 0.995 to give me the value of the normal distribution such that 99.5% of the mass of that distribution is less than that value, and I can obtain a 99% confidence interval now. Now moving on in practice, it's very seldom going to happen that I actually know sigma. What's going to go on in practice is that when I summarize BMI 1, in practice I'm going to use the sample standard deviation S when I construct my confidence intervals. I'm not actually going to use sigma. To construct such a confidence interval, I'm then going to need to use the t-distribution, which we learned about in class this week. So to learn about the functions that STATA has related to the t-distribution, type help functions. You can click on density functions and go down to students t-distribution, and you can see that there are 3 functions built into STATA that let you calculate probabilities with respect to the t-distribution. The one we're going to use in this lab exercise is the inverse t-tail function. It's somewhat analogous to the inverse normal function that we learned about, except that the inverse normal function was the inverse of the normal function in STATA, whereas the inverse t-tail function is the inverse of the t-tail command in STATA. It doesn't make a lot of sense to me as to why they sort of switched the signs on those. Why isn't there an inverse normal tail? I don't know the answer to that, but it's just the way that STATA built it in. So now if I want to construct a 95% confidence interval for mu, this confidence interval looks a lot like the confidence interval we saw before, but now we're plugging in the value of the t-distribution with n degrees of freedom, n minus 1 degrees of freedom, such that we're going to end up with 97.5% of the mass less than that value of the t-distribution, and we're plugging in the sample standard deviation in here. So let's see how to do that in STATA. So to calculate this confidence interval in STATA, I say display my sample mean minus inverse t-tail, and now instead of 97.5, since it's the t-tail function that we're inversing, we now put 0.025 in here. So this is going to be the value of the t-distribution such that 2.5% of the mass is greater than that value of the t-distribution since it's the t-tail. And then we have 19 degrees of freedom, since recall that we're using a t-distribution with n minus 1 degrees of freedom, where n, our sample size, is equal to 20. And then it's times our sample standard deviation divided by the square root of 20. And so we obtain a 95% confidence interval for the mean mu. And this right here is the confidence interval that we would probably use in practice where sigma is unknown. So you can see that when we calculated this confidence interval, all we did is we used information from our sample and we assumed that BMI was approximately normally distributed, and using just that normality assumption, the sample mean and the sample standard deviation, we were able to come up with our confidence interval. However, that was a bit of a pain, basically. So is there an easier way to go about doing this in STATA? The answer, fortunately, is yes. If you want to calculate a confidence interval in STATA using built-in functions, go Summaries, Tables, and Tests, Summary and Descriptive Statistics, and then go to the normal CI calculator. So remember, we're assuming normality, so we're going to use the normal confidence interval calculator. And I can say my sample size is 20, my sample mean is 25.0295, sample standard deviation is 3.184407, confidence level is 95%, hit submit, there you go, and I obtain the exact same confidence interval that I got before. So you can see exactly what STATA is doing when you run this CII command, and it automatically spits out a confidence interval. Because you took this course, you know exactly where that confidence interval came from. Now, does it actually get easier than this to make a confidence interval in STATA? And yes is the answer. So to just calculate a confidence interval from data that's already read into STATA, I can again go Summaries, Tables, and Tests, Summary and Descriptive Statistics, and then just click on this confidence intervals. And you see this window pops up, and the command that we use is CI. I'm assuming that it's a normal random variable. The variable I'm interested in is BMI1, and I want a 95% confidence interval, as you can see down here. That's the default. And I hit submit, and you see before when I used the calculator in STATA, the CII, I had to feed in my sample size, I had to feed in my mean, and I fed in my sample standard deviation. Now, if I just tell STATA, calculate a confidence interval for BMI1, it'll spit out that exact same confidence interval that we saw before. So in practice, it's really the CI command that you're going to be using very frequently to construct confidence intervals.